All right, welcome to Pre-AP Chemistry at Home. I hope you all are doing well. I'm going to divide up this chapter into, I don't know how many videos, quite a few. It's kind of a long one, but we'll take it little bits at a time. Hopefully the readings that you did for the AMI days will give you a jump start on this. So we're talking about gases, but in order to get to gases, we've got to talk about all the states of matter. And this is one of my favorite units because it helps make sense of a lot of things that you see on a daily basis but haven't really thought through. So first thing we've got to talk about is kinetic theory. You read about this, but kinetic obviously is talking about motion. And the idea of kinetic theory is we're just talking about how the particles of a gas behave. Okay, so the energy an object has because of its motion is called kinetic energy. According to kinetic theory, all matter consists of tiny particles that are in constant motion. So, in other words, everything, solids, liquids, and gases, the particles that make those up are in constant motion. And so you can measure the kinetic energy of that, and how much kinetic energy those particles have will contribute to what state that thing, that substance is in. So, according to kinetic theory, we pretend that the particles in a gas are so small that they have insignificant volume. So obviously they're going to take up space, but we're pretending like they don't to make the math easier on us. The motion of the particles is rapid, constant, and random. All collisions in a gas are perfectly elastic, like I said in a previous video. What this means is when a gas particle like hits a wall or something, it's not going to lose any energy when it bounces off that wall. That's what we mean by completely or perfectly elastic. Now, in reality, it's not like that, but it's going to lose so little energy when that happens that we can pretend like nothing is lost. So just kind of pictures demonstrating what we're talking about here. Gases always fill the container that they're in, and so sometimes it'll take a minute to spread, but eventually it will always fill that container. Now, how does kinetic theory explain pressure? Well, what is pressure? Pressure is the force that comes from the gas particles pushing on the container from the inside out. So when you have a balloon, what's the reason why your balloon inflates? Well, it's because you have blown air into that balloon, and now the gas particles inside the balloon are pushing from the inside out. They have a certain amount of force they're exerting. The more particles, then the more push it's going to be able to give, and therefore the balloon's going to get bigger. The same is true, like if you heat up the balloon, but you don't change the amount of gas, you're going to get more energy, so those particles are going to give more force, and your balloon's going to expand. You put it into the freezer, it's going to contract because they're not going to have as much kinetic energy, so they're not going to push on the balloon with as much force. Atmospheric pressure is the pressure of the atmosphere. So obviously our atmosphere is made up of gas. Those gases are constantly pushing on everything. So for instance, when you blow up the balloon, what you're doing is you're introducing a gas on the inside of the balloon that's going to compete with the gas on the outside, the atmosphere. So the more gas you put on the inside, the better it's going to be able to push against the atmosphere on the outside. So that's kind of neat. Gas pressure is the result of simultaneous collisions of billions of rapidly moving particles in a gas with an object. So just keep that in mind. There's atmospheric pressure, which is also gas pressure, and then there's like gas pressure of individual gases that we might be dealing with. A barometer is how we measure atmospheric pressure, and I explained this in a previous video. Essentially, we just invert a tube filled with mercury into a container with mercury, and there's going to be a vacuum in that little tube, and so when we invert it, however much the pressure is pushing down on that liquid in the container, it's going to push it up the tube. So the height of the mercury in the tube will tell us how much the atmosphere is pushing. So if you look at sea level, there's greater pressure than on top of Mount Everest. Well, what's the reason for that? There's less gas on the top of Mount Everest the atmosphere gets more and more thin as you go up. So less gas, less pressure. That's called a barometer. There are a whole bunch of different units to measure pressure, gas pressure. The SI unit is the Pascal. We don't use pascals a whole lot, to be honest with you. It is the SI unit, but we will use kilopascals. And yes, that is just like converting to kilometers or whatever. And then there's atmospheres, there's millimeters of mercury. All the conversions are in your book on that table, but here's the three main ones that you will need. One atmosphere is 760 millimeters of mercury, which is 101.3 kilopascals. Torr and millimeters of mercury are the same thing. Bar and ATM are almost the same thing. They're close enough. So to convert between units, just use sideways dominoes like we've always done. This one says you have 450 kilopascals. What's the measurement expressed in atmospheres in millimeters of mercury? So if you look at the math here, 101.3 kilopascals is 1 atmosphere. So just cancel your units. You get 4.4 atmospheres. Then our next one, you're going to millimeters of mercury. Cancel your units. Set, the ones equal to one another that are in that table. And you will get the answer. I think that's going to be my stopping point for the first video. I hope you understood everything. If you don't, just shoot me an email and I'll see what I can do.